Okay. Did all of you get a worksheet as you came in? We've got more over here. A lot more up here. So there you go. Okay. You guys having a good day? One of the other students said it feels really nice outside, and I told her that's probably why I've had a bad day, because I've been stuck in my office all day. But now I'm here with you guys, and I'm doing better. So, you should have got an email with your exam 1 and your score. Nice job. The mean was just under 85, the meaning 87. As a whole, really impressed. Good job, you guys. Way to study hard. So, if you didn't get one, then let me know. We will get the scores up on Learning Suite soon. So you'll see the score even if you didn't get the email. But. Okay, who'd like to start us off with a prayer? Thank you. Amen. Thank you. Okay. Yeah. So there's worksheets. If you didn't get one, there's one right here. I'm gonna grab that. For those of you that are online, it's on Learning Suite. If you go to pre-lecture material, you can download it and start doing the problems. So I'm going to turn you loose on these problems. When we'll come back together, we'll talk about some things, and then I'll turn you loose again to do more. Yes? Oh, thanks. Yeah, thanks. So there's a typo on here. You're supposed to stretch it in the x direction twice. That's not what it's supposed to be. Pick one of them to be the you can say pick 3 times in the y direction and 2 times in the x direction. So one's supposed to be x, one's supposed to be y. Doesn't really matter, but 3 in the x makes a little more sense because it's a wide smile. But that's what I was thinking. But you can pick whatever one you want. So. All right. Really quick, a lot of students last class, they really struggled with this. So you guys are really good at translating this transformation written this way into a matrix. So a lot of you have written a -1, 0, 0, because there's no x's in the new y and new z line. I have 2 y's, a -y's, 0 y's, and no z's, a -5 z's, -1 z times x, y, z. Okay, so a lot of you have done this or know how to do this, but that's not what we're trying to do in this particular problem. We're trying to prove it from the definition and show that it's linear. So a transformation T is linear if it satisfies these two properties. So I should have 1, 2. So if the transformation of the sum of the two vectors is the same as the sum of the transformation of those two vectors, and if the transformation of a scalar multiple of the vector is the same as the scalar multiple of the transformation of that vector. So to prove these, you have to pick arbitrary vectors. So I started off the first one here and the second one for you. I'm going to pick u and v, and I'm going to let them be just two arbitrary vectors, x1, y1, z1, x2, y2, z2. And u plus v is going to be this thing, the x1, the two x's added together, the two y's added together, the two z's added together. And now I'm going to put these in the transformation. So this transformation, the new x takes the old x, subtracts it, and adds 2 times the old y. So, well, here's my old x, here's my old y. So I take the old x, subtract it, and take 2 times the old y, and I add that there. The new y is the opposite of the old y. Subtract the old y, subtract 5 times the old z. So I subtracted the old y, it's this pair, subtracted the old z, and the new z is the opposite of the old z. So I've rewritten it this way. What do we do from here? Eventually, we've got to get to this to show that, hey, that's the same as T of u plus T of v. What are we going to do? What do you mean, plug in there with your vectors? Oh, so you're thinking like, oh, well, that can actually help you, and it helps you to realize what you need so you can start working backwards. So you can, hey, see, what's T of u? Well, T of u, it'll be this thing, except I'll have a sub 1 on all these. I'll have x sub 1, y sub 1, y sub 1, z sub 1, z sub 1. And T of v, I'll have sub 2's everywhere. So eventually I need to have those two things added together. Okay, but how do I get there? Yes? That's exactly right. We want to separate all of our y1s and all of our sub 1s and all of our sub 2's. So distribute these out, rearrange things inside, so you can rewrite it as all of the sub 1s plus all of the sub 2's. Then you can write it out as the two vectors, and then you can get this. So, and you do a similar thing here. You write it this way, then you write it in the transformation, then you do the algebra and pull out the c. To eventually you just have c times this. So hopefully that's enough to get you started. So go ahead, keep working on that, work on the other problems. Does anyone else not have a worksheet? So on part B, I did don't worry about trying to figure out how to do that translation. It's not that hard. You just have to add 1 to all of the y coordinates on all those points. But I just tried to shift it into a place that might be easier for you to think about. So don't think about, you don't have to worry about doing the translation and doing it back. The thing I'm trying to avoid is when you do some of these transformations, it might move well out of place. And so then you would have to, at the end, move it back, which is fine. But just focus on the linear transformations right now. Has anyone got C or D or E? You've got C?
Is that right, or did I flip something?
All right, let's start talking about these and going through these. So first we have this proof. So we're going back to the definition of a linear transformation, and the definition is that this has to hold these two properties, that the transformation of the sum of two vectors is the same as the sum of the transformation of the two vectors. The transformation of a scaled vector is the same as the scale of the transformed vector. So to do the first one, I pick two arbitrary vectors. I'm not just going to pick like 1, 1, 1 and 2, 3, 4 or something, two specific ones, because I'm not sure if those two specifics will work here, but others will not. So I have to make sure it works for all of them, I have to pick two arbitrary ones. So I picked some x1, y1, z1. So this is any arbitrary point in R3, x2, y2, z2. That's another arbitrary point. And I got the sum of those, u plus v. It's this new vector. And I applied this transformation to this vector by substituting in. This x1 plus x2 went in wherever there was an x. The y1 plus y2 went in wherever there was a y. The z1 plus z2 went in wherever there was a z. So I get this. And now we distribute out. Distribute out the negative, distribute out the 2, distribute out the negative, distribute out the -5, and rearrange. So I can get all of the y1s together and all of the, all of the sub 1s together and all the sub 2s together. And now I can rewrite this as the sum of two vectors right here. And this is exactly T of u, right? If u is x1, y1, z1, and I just plug in x for x, x1 for x, y1 for y, y1 for y, z1 for z, then I get this. So that's T of u, and likewise, this is T of v. Okay, so that proves the first part. Questions about this first part? Okay, and so similarly, and I made a mistake, I wrote x1, x2, x3 here instead of x, y, and z. So that was my bad on the notation. So this one looks different than this. I should have just had it. I meant to do x1, y1, z1, but you can also, since I only have one x, one y, and one z here, I can just do x, y, and z. I don't have any other x, y, and z's to distinguish it with. So I substitute in to all my spots. Wherever there was an x, I plug in cx1. Wherever there's a y, I plug in cx2. Wherever there's a z, I plug in cx3. So I get this. And then I pull out the c from this. And then I can use the vector properties, pull out the c from all of that. And this is just T of u, where u is x1, x2, and x3. So you can pull it out. So you get it in by substitution, but you pull it out with the properties and show that they're the same. Okay, questions? Okay. All right, so the first one where you're reflecting along the line, you're reflecting along the y-axis. You need the eye and the eyebrow to get over here. So the z coordinates are going to be this. I'm sorry, z coordinates. The y coordinates are going to be the same, and the x coordinates are going to change sign. So a lot of you are good at just reasoning through what's going to happen with these shapes and coordinates. A lot of you might want to use the power of the theorem, this powerful theorem that says you only have to look at where the basis vectors go. And then if you know where the basis vectors go, you use that to build your transformation matrix. So 1, 0 here, 0, 1 here. If I reflect along this axis, where does 1, 0 go? It becomes, the 1 becomes a -1, so -1, 0. And if I reflect along this line, where does 1, 0, 1 go? It stays the same, 0, 1. So my new transformation matrix is just a minus 1, 0, that's where my first basis vector went, and 0, 1, that's where my second basis vector went. So you can think about what happens to your x coordinates. Oh, my x coordinates are going to change signs, and my y coordinates are going to stay the same. And then you can think about matrix multiplication and what you need for that. Right? You need to have xy becomes a negative x and y. So you can think about, okay, so I need a negative, this to be a negative x, so this has to be a negative 1, no y's, and I need this to be the same. So you can, yeah, once you know this, once you understand this, you might be able to build this. And that's great. Or you can think about the power of this theorem that says I only have to figure out where 1, 0 and 0, 1 go. And I don't have to worry about an arbitrary x and an arbitrary y. So, okay. So B here, we're going to turn it upside down. We're going to stretch 3 times in the y, and we're going to stretch 2 times in the x. So here, then all 3 of these. And then we're going to compose them. We're going to put them together. So we're going to turn it upside down, stretch it 3 times in the y, stretch it 2 times in the x. So each of these you can get by doing the same thing, the same thinking that we did up here with these basis vectors. Think about where does 1, 0 go? Where does 0, 1 go? Yes? It does usually matter what order it goes in. So if we wanted to do this one first, this one second, and this one third, we're actually going to multiply them in a different order than what got done up here. In this case, it actually doesn't matter. You get the same thing in this particular case, but we have to be careful because sometimes it does. So what's the order? So if I'm doing this one first, I need a place to write this down. Okay, if I'm taking an arbitrary xy and I'm going to reflect it first, so flipping it upside down there, 1, 0, 0, minus 1. I'm going to do that multiplication first, and then I'm going to get something out, and then I will stretch it by 3 times the y, so 1, 0, 0, 3, and then I'll do it by stretch it 2 times in the x. So this is the order that it would go in. So this is my first one. This is my second transformation. This is my third. Now in this case, you do get the same thing, so it doesn't matter in this particular one. But that can seem backwards to us because we're used to reading left to right, where this, this, this. But since we're doing right multiplication, the vector we start at with is on this side. So this needs to be next to this, which is next to this, which is next to this. What order you do multiply them in doesn't matter. I mean, in the sense that I can do this calculation first, and then I can do this calculation. You know what's left in that. I can do the associative property, but I have to have them in this sequence. Yeah. Okay. Great. Okay. Other questions about this one? Yes. Yes. Yeah, so that question was, how do you know on the test which would come first? They'll tell you, or just take it in whatever order they say the transformations are. Yes, so this is the first transformation, this is the second transformation, this is the third, etc. Good. Okay. Other questions? Okay, how about this one? So we're tilting the head 30 degrees. So he can say, huh, what's going on, Brother Corey? So how are we doing this? So the idea is use some geometry, use some trigonometry. Some of you had this memorized or tried to memorize it, memorize a formula, which is, I don't have it memorized, or I only can write it down just because I derived it last class. So, but I'll show you where it comes from, so you don't have to memorize it. So, so here is a basis vector. Here is a basis vector. So I have to just think about where does the end of this basis vector end up when I rotate it 30 degrees? Where does the end of this basis vector end up when I rotate it 30 degrees? Well, that's going to be a 30, 60, 90. I'm just going to blow this up a little bit so it's easier to see. So this is 30 degrees. This is 1, it's length 1, because we started with something that's length 1. And I can use my, my trigonometry, or it's a 30, 60, 90 triangle. So you can use the ratio of the sides. The ratio of the sides is 1, 2, and the square root of 3. But this side is actually 1, so I have to divide everything by 2. So 1, 1/2, square root of 3 over 2. So the new coordinate here will be, my new x coordinate is square root of 3 over 2. My new y coordinate is 1/2. Okay, so that's for my first basis vector. 1, 0 goes to square root of 3 over 2, 1/2. How about my second basis vector? So I rotate it 30 degrees. Where do I end up? I'm going to drop a perpendicular. I get a 30, 60, 90. This is my 30. So I can write down my 1 to square root of 3 ratio. But this really isn't 2. It's really 1. A lot of you know your trig triangles better than me, so I always have to draw them out and scale them. So, or you just have sine of 30 degrees memorized, like I don't. So, so this is a negative 1/2 though this way. So I need to make sure I get that in there. So where does this one go? It goes, x is a negative 1/2, and y is a positive square root of 3 over 2. So, and that's exactly what happens here. The E1, nice notation, the E1 vector, E2 vector, this is the elementary basis vectors. So where do they go to? They go to exactly what we figured out. And the process, like you can just prove this in general with exactly what we did there, as long as you know something about the unit circle. Arbitrary 1, arbitrary, I mean, yeah, so 1, 0, 0, 1, and pick an arbitrary theta. Oops, shouldn't quite be that long. And an arbitrary theta. And where did this go? Well, this length is 1. You may remember from the unit circle, this length is sine, oops, didn't mean to write negative, sine of theta. And this length is cosine of theta. So the coordinates are for this, where this basis vector goes here, the coordinates are cosine of theta, sine of theta. And then you do the same thing with the second one. The trick here is this is theta. You have to do the transversal thing. So this is theta, this is 1, so the opposite side is your sine, and it's going in the opposite direction, and cosine theta. So you get a negative sine cosine of theta. All right. That's a perfect example of something that the book talks about and that I would never memorize. I would just, I mean, if you want to memorize it, go ahead. But I just understand where it comes from and then I can derive it if I need it. It's a much better strategy. It's a lot harder to keep track of all those things when you just try to memorize them and they're not connected to things. So, okay, questions about this one? All right, how about this one? Okay, this is a nice one. So we have our basis vectors. It's really shorter than this, but I'm just doing this to emphasize, to make it so we can see them. We can do the same strategy. There is a formula in the book. Again, you can memorize it if you want. Or you can just apply the theorem and think about where do these go and use what you know about projections. So So where does this go? Well, projections will go perpendicular. So this is 90 degrees right here. And I know something about how to find a projection. I hope you remember. I know you did already take the test on this, and so it's probably out of your head now, but you did know it at one point. How to project one vector onto another vector. So one of the keys here is I'm going to not think about this as a line, but think about it as a vector. So writing it as 10(1) is nice because then you don't have to worry about the decimal. You could write 1 and 0.1, but this way it's a little bit easier on the calculation. So now you can do, I'm going to do it just a little bit different than that. I'm just going to stick with my basis vector. So my basis vector is 1, 0. And I dot it with, I'm projecting it onto 10(1), 10(1), and 10(1). Ooh, not a lot. I need a stretching transformation down here on the board. 10(1), 10(1), all times 10(1). Okay, so this is just the u dot v over v dot v times v. So this is just the projection formula that you studied really hard to know. And what do you get out? Up here you get a 10. Down here you get 101. So you get 10 over 101 times 10, 1. And you can see that's where they end up rewriting it and they multiply in by the 10. But yeah, they do an arbitrary xy instead of just thinking about the standard basis vectors, which is just fine. So, and then we can do the other one. I can project this down perpendicularly to here, and I replace this with 0, 1. Everything else is the same. I get a different basis vector, and then I can write that. Sorry, I get a different transformed vector, and I can write it down. So, okay. Do you really get a negative in there? Where's the negative come in? Oh, sorry. I thought I was thinking that was still on the right, and I was like, where does that come in? Okay, so this is, yeah, okay, this is for the line on the other side that has a slight slant. So the lines, the sleepy eyes look like this. That's the idea. So maybe not quite that slanted, but. It's having a nightmare, I guess. I don't know. Okay, now you know I didn't go into art. Okay, we might not get to the last problem. I just have a few things to mention. I can make a video for that last one about the shearing. That's not as important. The projection is much more important. Unless your name's George, I guess. I guess no one knows who George Shearing is, but okay. I forgot to share this yesterday. Even someone in this class asked what an application of change of bases are. So so if you're dealing in animation, then you do change of bases to change your camera angle, to change the view. So so every time you want to think about rotating your object or moving your camera so it looks different, then you're doing a change of basis. Technically, it's a change of basis in 4 dimensions because there is a translation involved with moving the camera, but they have this trick called homogeneous coordinates where they can do it with as a linear transformation in R4, and they take a shadow of it into R3. It's kind of really cool. But this is one of the things that's useful. And in general, if you think about like flying something, you have a drone. A drone has a natural up, right, left, and forward and back. Right? That's going to be its coordinate system it works from. You're on the ground. You have a different forward, back, left, right, up, down. And so you have your system. And so you have 2 natural systems there to keep track of distances and coordinates. And you might be translating between the 2, or if you're a fighter jet or something like that. The jet has its natural coordinate system, and then people on the ground have their natural coordinate system. Might be, north, south, east, west, and away from the Earth towards the Earth, stuff like that. So those are analogs to change of basis. Okay. So linear transformations, I think I mentioned this yesterday in this class, but they keep lines as lines and they keep the origin fixed. Those are all of the linear transformations. So you can't take a line to a curve. You can't. There are transformations that do that. They're just not linear. You can't model them as a matrix multiplication. And translations are not linear, but I did mention this trick doing homogeneous coordinates that they use all the time in robotics and 3D animation, so that you can keep everything as a multiplication. So all of your scaling, all of your movement, all of your rotations, all of your camera angles, all of that just becomes one big massive product to do a bunch of stuff. So a lot easier than having an addition in there to do the translation that you need. And then all possible linear transformations can be written as a matrix, and all matrices are linear transformations. Compositions, we did already talk a little bit about compositions, about how if you have compositions, at least you have to multiply them in the right order. And the transformation that you do first is the one that you're going to multiply by your vector first. So it's going to be on the right side. You've seen compositions before. You've seen compositions of functions, and you're used to taking like an f of g of x. If you know what f of x is and a g of x, then you can plug wherever there's an x in f, you take the 2x minus 3 and plug it in to get 2x minus 3 quantity squared. You can do that also. This works with these transformations too. If the transformation of x gets a new x of x minus y and a new y of x plus y, and the transformation s gets a new x as 2 times y and a new y is 3 times x, then I can get the transformation s of t of x of y. So doing transformation of t first, that's supposed to be a little o, I forgot to change that, but s of t of x of y. I can do that by substitution. I can go back and say, well, if s is 3 of my old x, I can go back to my old x, which is x minus y, and plug it in. So I get 3 times x minus y as my new y. And if the new x is 2 times y, I can go back to my old y, which is x plus y, and plug it in. And so I have 2x plus 2y, 3x minus 3y. I can rewrite that as a product. And so that's the same as the matrix multiplication, 2, 2, 3, negative 3. But I can also then just separate out t and s, write them as a product of what they are, and then apply them together, I get the same thing. So you have a homework problem where you actually do this and go through it and show it. Okay. So I was already kind of using this language. There's another way to think about matrix multiplication. Kevin likes to think about it this way. So, I have a, b, c, d. I multiply it by a coordinate x, y, and I'll get a new x and a new y. Well, a, b, c, and d have nice interpretations. A is the contribution old x has on the new x. B is the contribution old y has on the new x. Right, so this ax plus by, that's the first line here, the a and the b. Those are going to tell me how to make my new x. So I take a times the old x and b times the old y, and I get the new x. And then c and d tell me how I'm going to combine those x's and y's, those x and y coordinates to get my new y. So c is the contribution of old x that the old x has on the new y. D is the contribution old y has on the new y. If you don't like this way of thinking, that's fine. I'm just throwing it out because it might be helpful. I find it somewhat helpful when I have something like this, 1, 1, 0, 2. I know that my new y doesn't depend at all on my x because c is 0. So it doesn't matter what coordinate I have in my x. My new y is going to just depend on what my new y is only dependent on my new y is only dependent on my old y. So, if it helps. Okay, any questions about anything we've done today? All right, have a great day. Don't forget the homework. The homework is written up on the board over on the side there.